So I've already done a talk on Bevy ECS. I was specifically dealing with the particular crate that Bevy has as its foundation for implementing the Bevy engine. The second part of this talk is talking about Bevy App. Now, Bevy App is a companion crate, which adds a bit more higher level structure around the ECS foundation. And together they form quite a useful foundation for Bevy engine as a whole. So we're going to cover a few things. We're going to talk about what is the Bevy app. We're going to talk about how the systems now access the world and the schedules that we talked about in the last talk. We're going to talk about plugins, which is a better way of structuring our code. We're going to talk about events, which allow you to signal other parts of the code at a distance. We're going to talk about runners, sub-apps, and states. Okay, but first let's catch up about what we talked about briefly in the last talk. So we talked about the ECS model, the entity component system model. We talked about the world, and the world just contains all entity components and resources. Components and entities represent the data aspect of an ECS system. An entity is just an opaque type that contains components, and components are data structures that derive the component trait. An entity can only have one instance of a component type. So you have a component structure called position. An entity can only have one instance of that position data inside it. This is because components and most stuff in Bevy is labeled or referenced by type. And then we have the systems, which is just simple functions. But even though they're simple functions, there are some constraints that all the parameter types that you pass to that function must also derive from the system param trait. It must implement the system param trait. If one of those arguments that you pass to the function or have in the function signature do not implement the system param trait, it cannot be a system. And also the parameters that you do use in those functions can determine the concurrency of a system. So if Bevy discovers that it can run two systems concurrently and in parallel, it will do that in parallel. There's also schedules. So schedules is what owns the systems. They're responsible for running code, doing that parallelism, and based on access patterns. And they make use of a parameter called commands, of a commands type that allows you to make changes to the world. But all changes to the world, such as adding entities, adding components to entities, are deferred, because otherwise you'd have race conditions. And there's a whole bunch of other features we talked about in the talk: bundles, system sets, run conditions, and we talked about table-based versus sparse set-based components. So hopefully you know all about this and you remember everything I said about in the first talk. So what is a Bevy app? A Bevy app contains a world. It also contains multiple schedule instances, and each schedule has a label. Now, a label is a type. It can be an enum or it can be a struct. And it also adds glue for managing plugins. Now, plugins is the way of modularizing your systems and your resources and so forth, and making things more reusable. It also implements the event system. This is how you can trigger events in one part of the code, and you can have other parts of the code react to that event. You have a runner function. This is essentially what might implement a main loop. And then you have system states. And Bevy app and Bevy ECS, they both have a role to play in system states, but you kind of need the Bevy crate, the full crate, to actually really use them. Again, the parameters determine the concurrency of the system, and an app contains a concept called sub-applications, which we'll talk about towards the end of the talk. So let's look at a hello world and how you might write a very small Bevy program using an app. I'm going to switch over to my VS Code, and right now this is the old ECS only way of doing a hello world. So I create a world. Remember, this contains all the components, resources, and entities. I create a schedule. This is what's going to run the systems. I add a system to that schedule, the hello system. This just prints hello Bevy. And then I tell the schedule to run using the world as a reference to all the entities and so forth. Now, this hello system is a minimal system. It has no parameters, so it'll run every single time you call run on the schedule. So if I run that, you can see how that works. But let's do it the app way. So we create an app. We add a systems, and we call run, and we can delete all this code. So remember, an app has a world, so we don't have to create that. It has a whole bunch of schedules. Why it has multiple schedules, I'll talk about later. And here I am. I'm adding a system to one of those schedules. Now, the schedule I've chosen to add it to is called update. This is the usual place that you add systems that you want to get run every single frame, every single update cycle, every tick. And we just run. And this, of course, exits immediately after doing one cycle of doing that. And hopefully, if I run it again, it will just work. There you go. So that's what an app looks like. So let's talk about systems, specifically access to the world and the schedules, like we did before when we're adding systems and so forth. You've already seen a bit of that in the program I just written right now. So the API to the app re-implements a lot of the APIs that are already in the world and schedule, specifically add systems, init resource, insert resource, those kind of things. But unlike the schedule, the app requires you to say which system stage you want to add. And a system stage is essentially a single schedule. And as I said, the app has multiple schedules, multiple stages, and we decided in the Hello World to add a system to the update stage. Now, a system stage, as it represents a schedule instance or a logical group of substages, there's a root stage that's called main, but you don't really interact with the main, but it contains all the other stages. But it also has special startup stages that are executed only once on the first run. So instead of adding to update, you could add to pre-startup, startup, and post-startup. So this is useful for performing initialization tasks. And you got some other stages if you want to do something before all the other startup systems run. And you can probably use post startup for running code where all the systems have run at least once. Then you have a whole bunch of main stages. You have a stage called first, where any system added to that is guaranteed to be run first. You have a pre-update, which is useful for plugin authors to make sure they run code before the user's usual update stage is called. We then have a state transition stage, which is used for implementing system states, which I'll talk about later. We have a run fixed main loop, which is a sort of a group of stages. And this essentially runs the fixed main stage as many times as is needed to catch up in a sort of fixed time step intervals. So when you're writing games, sometimes it's important to have a fixed time interval between your updates, mainly because of physics and some deterministic algorithms that you need to run. You have your update, you have your post update for plugin authors to run code after, and then you have the last one right there. I'm hearing some beeps. Do we have some questions?
I'm also hearing the beeps, but I think they're coming from your side.
Are they? God damn it. All right. I'll just ignore them. So let me show some stages and how that works in code. So here we have we're adding one stage right now, one system to a stage right now. Let's add another one. Let's call it goodbye system. And let's add a first system and a last system. Here we can use a similar interface we did before. We can say add systems to first system. And here we can use a tuple to add multiple systems here. And we can add the last one there, right there. Oh, there's supposed to be a comma there. Okay. I run that. And you can see that the first system is always run first, the last is always runs last. And if I do that enough times, sometimes you'll see the hello come before the goodbye. There you go, it's right there. So you can see hello comes before goodbye in this one, but the one before the goodbye became for hello because they are run in parallel. Bevy recognizes that there's no race conditions in running them at the same time, so it does. But all the systems in the first stage are run first, followed by update, followed by last. All right. So plugins. So plugins are just a better way of structuring code. In the code I've just shown you, I call functions directly on the app where I construct that app. But we can put a lot of that code into a plugin and then just add the plugin to the app when we construct that app. A plugin is a structure that implements the plugin trait. It provides a build method that allows communication with the app instance. So when you add a plugin to an app, the app will call the build method on your plugin. And you do that just through the add plugin method. We also have plugin groups, which is it allows plugins to be combined together and created together. The common one you would use, for example, is the default plugins, which will have about 10 to 15 other plugins kept together, like Windows, input, rendering, all that kind of stuff. And this is also added by the exact same method. So you can use the same method to add a single plugin or plugin groups. So we have a few built-in plugin groups. We have the minimal plugins, which is just bare minimum. It has a few systems to run timers and task pools. And then we have the default plugins, which is pretty much the whole basic Bevy engine. This will, when you have that, you will a window will appear. You can interact with the renderer by adding certain entities with certain components, and so forth. So what happens in a plugin, and what is its life cycle? So when an app registers a plugin, the build method is called, and by default, it should only be registered once. Now, build is the only mandatory method that you have to define in the plugin trait. All the other methods I'm going to mention here, they have default implementation, so you don't have to redefine them unless you want to. But if you want a plugin to be run more than once, I can't think of a reason why, but if you do, you can override the isUnique method and return false. Plugins are considered exactly the same plugin if the name method returns the same name, and by default, it returns a type name, the particular structure that implements that plugin trait. So the app waits for all registered plugins to return true when calling plugin ready. This is only useful for asynchronous plugins that, for example, maybe you're setting up a renderer and that's asynchronous. So build will return straight away, but in the meantime, ready won't return true until the rendering is set up. And then the app will call the finish method. which is useful for plugins that depend on other plugins in an asynchronous step. And then it will call cleaner, which is a secondary way of running code. So I'm going to show you a quick demo of how we could use plugins to organize the code we have right here. So let's say I want to have the hello and goodbye system in their own plugins. So I would and I will derive, debug, and plugin. Yep. And here, I implement a plugin for hello, goodbye plugin. I then do the build method, which takes an app, and I can interact with the app in the exact same way I did before. So add systems, update, hello system, goodbye system. Is it plugin? What's wrong with that?
If you're implementing plugin, you don't need to derive it, do you?
Yep, you're absolutely right. Yep, I'm doing implementation as well as doing a plugin. Well spotted. Thank you. Let's do another one for the first and last system. So let's. And we can. Come on! He's going to do it. Brilliant. Look at that Copilot. Never leave home without it. Right. So there's the plugins, and so I can go back to here and I can say add plugins, hello goodbye plugin, and I can add plugins first last plugin, and I can get rid of all this. Here we go. Run that.
A question, Matt. Is it okay to interrupt?
Yeah, you go ahead.
You mentioned that like the default plugins and the minimal plugin.
That's right.
One thing that I'm noticing, like when doing a custom build for the web with using a Bevy app, it's like, I mean, a small game would be like 50 megabytes. Using the minimal plugin, would that be a way to make the WASM files smaller, or are there any other kind of strategies to reduce the size? Because 50 megabytes is quite much for just a simple game, I would say.
Yes, the default plugins will pull in a lot of Bevy stuff, including input, audio, rendering. So it'll put in web GPU and all the code that defines what components do rendering. The actual renderer itself, which is quite sophisticated now, it will pull in logging. It will pull in some debugging stuff. There's a lot of stuff. It's basically say, I want the entire Bevy engine, and I just want to get going. The minimal plugins is literally just a few systems that help implement timers and task pools, so some of the more low-level aspects of Bevy can work. I talk a little bit about. Do I talk about times in this? Maybe not. But let's think about this. But you can look into the code. For example, can I do this? If I do default plugins, and can I do that? Here we go. So here you can see it's having a panic handler, a log, task pool, type registration, frame count, time, input, all the Windows stuff, and a whole bunch of things based on features. The asset manager, scene system. There's a lot of stuff, right? If I go and say minimal plugins and say function 12 on that, you can see there's a lot less. There's time plugins to support some time resources. There's a frame count. There's nothing there, right? You would only use that if you were going to write pretty much everything from scratch. Say you didn't want to use the Bevy renderer. Say you want to use your own libraries and so forth. So it would be a lot less, but you would never have any functionality. Okay. Now you can go in and add individual plugins yourself, but that's up to you. 50 megabyte for a full-blown game engine isn't that big, and I don't think so. But it does matter when you're running it on a web browser because you're going to download that 50 megabytes, right? I don't have much experience building games on a web browser, so I'm probably not the best person to answer your question or give you advice on what would you do better. So sorry, but I just wanted to show, moving on, the plugin group. Now I can't remember how to do this. I probably have to. Okay, let's have a look at plugin the build. What did I say it was? I've lost my windows. Here we go. Plugin group. Right, let's have a quick look at that. The plugin group builder. Yeah, there you go. So I apologize. I can't remember how to use this. Let's go back to. Right, yeah, now I remember. Okay, sorry about this. So you create a struct, say in my plugins. You then implement plugin. Is it plugin group? Yeah, I think I got the slides wrong. I'm going to fix those before I make them public. And then you do this. Let's have a look. Yeah, you just need to get rid of this. Where have I gone wrong? Oh, yeah. This is wrong. And that should be just a self. And then we create a plugin group builder we call start, and we pass in our self, and then we then add this. So now I can go back to the main, and instead of adding these two, I can just do my plugins, and hopefully give it that. Thinking takes so long. And there you go. So okay. Okay, so yeah, so you define a struct. It derives from the plugin group. We call start on the builder. We then add the plugins until we have all the plugins, and then we just return that. Okay, so moving on to events. Now, events are was part of the observer pattern. An event is something is a form of communication at distance. Essentially, what happens is that a system will trigger an event. For example, maybe an explosion event in your game, and you want other parts to react to that explosion. So maybe all monsters might react to that explosion event, find out if they're close enough, and then apply damage. One system will send an event that other systems can receive. But events are controlled by event writer and event reader types. They are both derived from system param. They implement the system param traits, so you can use them as system arguments. So that gives you access to an object that can either send or receive events of a particular type. Now, an event is simply a struct, so or an enum, and then you register the event with the add event method in your app or in your plugin. So one system will use an event writer to send we call send to produce an event, and the other systems will use the method read to read the incoming events. But there are some pitfalls with that. If the receiver system runs before the sender, remember in the ECS you can control certain ordering, and there are multiple system stages to control ordering. But if you make a mistake and a receiver system runs before the sender, what's going to happen is that the receiver will not receive that event until the following frame. There'll be a 1 frame lag. So you kind of want to make sure that all your senders send events before the receivers if you don't want that. However, the application will keep events around for at least 2 frames, and then it will just silently destroy them. This gives you enough time to deal with that 1 frame lag if you don't care about that. Also, the one thing to look out for are run conditions. Now, systems can have run conditions attached to them for the normal ECS system. And what that means is that another system will determine whether the original system can run or not on that particular tick. Now, this means that certain, if you attach a run condition to a system that is reading events and that system does not actually execute, then you do not read the events. So it is possible to send an event and have nothing respond to it because the run condition stopped it. This could miss the 2 frame window, and therefore the event will come and go, and you'll have a bug where nothing will respond to it. So if that is an issue, then you need to implement your own custom event system on top. Kind of have another system that will never have run conditions, will queue up some of the events and store them ready for the actual real system to process the event to actually kick in. So how it works, when you register, when you call the add event, Bevy will create an events resource. This acts as like a backend storage for an events queue, which is actually a simple vector. And it will also add a system to clear those events periodically. So it's kept for 2 update cycles, as I said, or the 2 fixed step cycles, whichever is longer. Because remember, a fixed step can happen multiple times in a single update loop, depending on how long things take and how frequently you want fixed steps to happen. So the event writer will access the events resource. So when you send that event, it is just written to that vector inside that events resource. The event reader will then access events immutably, but it will store an integer counter to keep track of how many events have been read for that particular system. This is why both the event writer and the event reader need to be immutable in your system parameters. So This turns out to be a lot more performant than the change detection that I talked about in the original talk, where you can add a system with a particular kind of query, which will only get triggered if and when an entity changes, a component changes, etc. There is a built-in event already in Bevy, implemented in the Bevy app crate, and that's the app exit event. So to finish a normal Bevy application, you just send the app exit event. You can do that through an exit system. Obviously, this is just going to exit straight away. There's no logic around it. But here you can see that we have the exit parameter, which is an event writer of app exit is mutable. And we just call send, and we pass the app exit success value. App exit happens to be an enum. So runners. So runners is something you probably don't need to worry about or work with. But essentially, when the app runs, when you call run on it and all the plugins have been set up, it will run a particular function attached to your application. And there is a default runner, which just updates all your schedules just once. But sometimes you might want to do a main loop, right? For windowed applications, you'd have an event loop inside there. Fortunately, Bevy comes with Winit plugin, which does just that. It uses the Winit crate to create a window, and then it implements the event loop, which means that when you call run on the app won't exit straight away like it has been doing on the Hello World examples that I've been doing there. So how does that work? So app run does two things. It rebuilds the application, which basically means restarting the plugin lifecycle. This means calling build. This means waiting for the ready, calling finish, calling cleanup. And then when it does that, it will call the runner function that is set up by the method called setRunner. Now, there is a default. I haven't called setRunner in my code so far, but as I said, something like the Winit plugin will have called setRunner to override the runner, which is just a basic function to handle the event loop. Now, in iOS and Android applications, it's important to note that app run will never exit. That's just the nature of mobile apps. Mobile apps generally are killed through operating system events, saying, okay, I'm about to kill you. So shut down and close your files and do whatever you have to do, and then I'll just kill the process. With mobile apps, you don't exit the applications themselves. They run until the system says there's not enough memory. As I said, default plugins provides the Winit plugin, which implements the runner for Windows events loop, and which basically means that the application will not exit until you close the window or send the exit event. So the runner function is just a simple signature, takes an app and returns an app exit. An app exit is an enum that has a success or that has an error with a non-zero you wait. This basically is mapped to the return code from the process. The success will be 0. So if you write your own runner, you should handle the plugin lifetime by checking the plugin state, calling plugin state, asking whether it's ready. And if so, then call app finish and app cleanup. And then within the runner, you should call app update at least once, or in a loop. So sub apps. An application can contain sub applications. Sub applications contain their own instance of a world structure. So you can see the diagram here. You have your main app, it has its own world. And then inside there is a bunch of sub apps you can have. Now, this is useful for situations where processes need to be kept independent from the main application. Bevy does this for the renderer. So it has the same API as World and App for adding system resources, etc. And the main feature of a sub application is the extraction function. This allows you to synchronize the sub application to the main world. Now, the renderer does that in Bevy by looking at all the entities and components related to rendering in the world, the main world, and then construct a new set of entity and components specifically for managing this rendering in its own world And that way it essentially snapshots your higher level version and creates its own lower level version to drive the renderer. So the extraction function is a simple function that takes the two world parameters. The first one is the main world in the app, and the second parameter is the subworld. And essentially they're both mutable, so you can mutate either of them. You can either set stuff up in your sub app world, or you can return feedback back to the main world. It's up to you. And it's called once per update, after the main world update, but before the sub app updates. And you set the extraction function with the set extract method in the sub app. So how do you do that? So you create an instance of sub app with sub app new. You add the sub application to the application with the insert sub app method. And that requires you to pass in a app label. Now, an app label is just a struct. As I said before, Bevy uses types for labeling stuff. So this acts as a key. So later on, you can call get sub app or get sub app mute with that key and get a reference to that sub app that you previously inserted. And then you must make sure that you do actually set the extraction function when you create that sub app. So we already talked a little bit about why. As I said, Bevy rendering makes full use of this. States. So Bevy implements through the Bevy ECS, Bevy App Crate, and the Bevy Main Crate. Is able to implement finite state machines for systems. So a state is an enum. So you can imagine enum which have invariants such as in menu, in pause menu, in game, and you want those to say which part of your game you're in. So when you hit the pause menu, you might go from the in-game state to the pause menu state. So what happens when you implement system states? So you essentially need to add a system to the relevant system stage to react to state changes. So, for example, say I have a system that says, okay, when I press the escape key, I'm going to go into the pause menu. You need another system to say what happens when you enter the pause menu. And so you would add system, call the add systems call, but the system stage you would use would be on enter, passing the enum type, which is your state machine. And you could do the same for on exit. So whenever, if you need to do some work, when you exit the pause menu and go back to the game, for example, you can add a system to the on exit that, and all systems on that will get called when that state change happens. So that's reacting to state changes. To actually decide whether a system is run only when a particular state is enabled, you can use run conditions. So you would use run if, and then you use the system called in state, which basically returns true if the game is currently in a particular state. Finally, you need to register the states as well. So you call the inner state method, which is a generic method based on your enum. And what that will do under the hood, it will create two resources, the state and the next state resources, and you can reference them directly in as system parameters. And the state parameter will just access whatever the current state is. So if you're in a game and you're about to go in the pause menu, that will return in game. The next state is what you use to say, okay, I want to transition to this state. So if you're reacting to the escape key, for example, you would use next state set to say, okay, I want to set it to my state's pause menu, for example. And that's basically all the features for Bevy App. Beyond this, we start entering the area of the high-level specific plugins and systems and resources that make up the Bevy engine as a whole, such as audio input, asset loading, scenes, rendering, all that kind of stuff. and that's a much more bigger topic. So ideally, the conclusion, the summary is that the ECS and the app work really well together to provide this really powerful but straightforward, reasonable, easy to understand foundation that a powerful game engine can be built upon. So what's next? On my next talk, if you want to, I can take a deep dive into the renderer, or we can talk about some advanced features of Bevy, such things that we haven't talked about in the ECS, such as one-shot systems, exclusive systems, or we can take a deep dive into non-render-based default plugins, for example, audio input, asset management, timers, logging, that kind of stuff. Please message me on Discord, give me some ideas of what you want to hear about next. I'd be very happy to plan a talk, and maybe I have to do the research to actually educate myself on these systems as well. Thank you. That's it. That's my talk.
Thanks, Matt. That was great. I enjoyed that.
I hope I didn't overwhelm too many people. I kind of burst through that quite a speed. Are there any questions? Oh, I've got some questions down here as well. Oh, Kira's doing a lot of research.
But one recent one in the chat, how long would it take to implement something like Flappy Bird in Bevy, would you guess?
Oh, if you knew how to implement Flappy Bird in any other language, it'd probably be really, really quick. Like just drawing sprite to the screen is essentially, you create an entity, you add the relevant components. I can't remember the top of my head what they are, but there'd be like some sort of texture component. There'd be there'd be some sort of positions. But you would define a bundle that represent your Flappy Bird. For example, you'd have a bundle that represent the pillars, I guess, and you would render tiles. Essentially, you would create entities per tiles, and then you'd have a system for each logic, right? So a system for reacting to input, a system for reacting for comparing the position of Flappy Bird with the pillars, the system for just applying gravity to Flappy Bird if you're not pressing anything, that kind of stuff. So that's why I like ECS systems, because features of the games map directly to a single or just a few systems that work well together. Anything else? Oh, you talked about the optimization level and size and stuff like that. The stripping, yeah, stripping symbols is always a good thing to do. Nice one. I think that's it. Any other questions?
I guess one thing for folks who missed, I think you mentioned it in your last talk, but maybe not in this one. Bevy provides a set of examples that if you are looking to get started, you might want to play with.
It does. Yes. I was going to try and, if you go to the crate, crates.io, find Bevy, there'll be a link to the GitHub repository. And inside the root of that folder, there'll be an examples folder. If you know how to use Cargo, you can run Cargo with the -- example flag and the name of the .rs file in the examples folder you want to run. Without the .rs, maybe I should share my screen again. And oh, I don't have Bevy installed. That required downloading. But if you know how to run examples, as I said, Bevy has a ton of examples.
There's a site I've linked in the chat as well where they're already ready
Brilliant.
to run in the browser, which is handy with the code below.
But I've noticed that a lot of Bevy tutorials and Bevy concepts don't actually talk about the foundational stuff. They don't talk about using the world separately or using a schedule separately. and what happens behind the scenes. Now, there is a Bevy cheat book, Bevy cheat book. I'll finally reference the URL for that. This is a really useful resource. And there's a ton of stuff in there about things I've talked about and a lot more. If you're interested in playing around with Bevy, I recommend looking at that. Bevy is a pleasure to use. One of the reasons it's a pleasure to use is that the foundational stuff that you have to deal with all the time is a pleasure to use. The APIs are very ergonomic. You saw how I added systems. If I added more than one system that I want to run in parallel, I just stuck them in a tuple. How nice is that? Or not? In the original ECS talk, I talked about how you can do ordering and sets, and you can say, I want this to run before this system and so forth. It's just so beautiful. There's not a single ECS system out there that I've seen which has a better API than Bevy. And you can take Bevy App and you can take Bevy ECS crates and just use those and just build your own engine. If there's nothing else, I think that wraps it up. Right, Kira?
Yeah, thank you so much, Matt. Again, we had 2 topic suggestions if you do want to do another talk in the future of shaders and profiling. So,
oh yeah, well, specifically in Bevy or generally, because you've got the flame bench stuff, haven't you, in Rust about profiling? But is it specifically in Bevy? Because I actually don't know how to profile properly in Bevy, or how to do shaders in Bevy. So that would be a really good education for me. One of the things that I like about doing talks is that I get to go away and do some research and learn stuff. And I would advise anyone who's brave enough to get recorded and put up with this, hearing their own voice afterwards, to go in and do a talk for the rest of us, because you will go in and learn a lot.